So we have the next speaker, who is Vinícius Carvalho, and he is a PhD student in the Center for Neuroscience at the University Federal de Minas Gerais in Brazil. So Vinícius, it's all yours.
Okay, thank you so much for that introduction, Adeel. Can you see the slides okay?
Yes, we can see everything. We can hear you well.
Okay, great. I'm gonna skip the traditional what is epilepsy slides and just highlight that epilepsy is characterized by recurrent seizures. And by predicting or forecasting these events would greatly ease the burden of patients of epilepsy, whether by enabling the device of alarm of early warning systems that would warn the patient or their family that they have an incoming seizure and they could go to a safe space or something. And it would also allow to close the loop for real-time targeted interventions that could prevent the occurrence of seizures themselves. But this quest for the reliable seizure prediction or seizure forecasting systems has been marked by ups and downs, with some once promising methods that when faced with more real and clinical data and wider data sets didn't achieve as expected. So this has been actually termed as the longer winding road. But in the last few years, with some advances in technology, we have a lot of reasons to believe that we have promising prospects that reliable seizure forecasting systems might be achievable, at least for some seizure types. Among some of these reasons include the availability of long-term recordings and implantable devices, increasing number of public data sets, the use of individualized models of patient data, deep learning algorithms, and the one I'm going to focus on this presentation is the use of active probing paradigms for seizure anticipation. That's basically the idea that you can get more information out of the system by stimulating it and getting its response. So you can get a better picture of its dynamics and the states that the system is in than you would get just by passive observation. And we have some examples of this being used for assessing seizure susceptibility. Around almost 20 years ago, in the first use of this by Selim and Lopes da Silva's group with visual simulation. And throughout these years, we have some uses of this strategy with a few other groups, such as Differinson and Mark Cooks in Australia, even with patients with epilepsy. Our group has shown some uses of this in a rat PTZ, acute seizure model of pentylenotetrazole in a rats, that when we use simulation, we can see the temporal rearrangements of some specific waveforms right before a seizure happens, and that's not visible with passive observation. And this is without eliciting seizures themselves, so they have no proictal effect in this model. And also with auditory simulation, with auditory steady-state responses in a audiogenic rat strain model. So the objectives of this work is based on combining these two, is to explore different conditions in which this active probing approach is useful for highlighting the underlying parametric changes in a computational neural model that lead up to seizure. And we expect that our hypothesis is that as the model parameters are shifted from normal towards the ictal states, we would highlight excitability and synchrony features with the use of low frequency probing stimulation. For our work, we use the Wendling and colleague CA1 neuromass model. It's a macroscopic, mesoscopic, or lambda parameter model, akin to the ones pioneered by Lewis and Kelvin, Lopes da Silva, and Walter Freeman, in which we have specific populations, neuron populations, and we take the mean activity of each population instead of having detailed models of each neuron. And these, we have functions that rule the interactions between these populations, such as the wave triples that represents the postsynaptic potential to actual potential density of each population. And we have the pulse to wave function. That's the opposite, the actual potential to postsynaptic potential. That's, we have the specific impulse response functions for each population. That will be main cells, excitatory cells, that could represent pyramidal ones, and inhibitory interneurons that could be peridendritic, so they have slow dynamics, or parasomatic, so they act really fast. These would represent basket cells. And the inputs of the model is a direct actual potential density inputs, white noise, to the main pyramidal cells. And just by shifting these parameters, these excitatory and slow and fast inhibition gains, we can get that broad range of types of activity that quite resemble the real-time, real-depth EEG signals, ranging from normal background activity to sporadic and sustained discharges of spikes. We're going to focus on normal as we shift toward the ictal-like activity. And we have some other types of oscillations as well. We propose a slight modification to this model by coupling additional population sets through the main excitatory cells. And we rule this with a coupling in. And we add the additional inputs that represent the probing stimulation. That will be the low frequency probing stimulation. That can be either to one population or both. And as I mentioned, we can tune the excitatory gain of one or both populations within the one. We can decrease the slow inhibition gain and bring the system closer to seizure thresholds as well. And we can bring seizure data-like states by increasing this coupling gain. And this presentation, I'm gonna focus only on this one. That will be this one model setting that I'm gonna show. We have both populations. We measured the simulated activity of both. And we stimulate only one population while increasing the coupling gain. And we can also stimulate both populations simultaneously. Here we have some other simulation parameters. As I mentioned, the probing, active probing approach is a low frequency one. So every 2 seconds, we give 10 milliseconds burst. And we vary this with each iteration, with each simulation, ranging from 0, that would be the passive case, the passive observation case, with steps up to 200 pulses per second. That will be the incoming, resembling this inputs. Yep. As I mentioned, we have this gradual parameter shift to bring the population near the ictal threshold by increasing the coupling gain. We have tested the other combinations as well, and we extract features after each simulation. So we have the variance, skewness, kurtosis, the lag-month autocorrelation, and the mutual information between the activities of both populations. So we measure synchronization between them. And we can measure the effectiveness of the probing approach. We can see that there is an incoming seizure, or we can see the underlying parameter change. If these features are correlated with either time, the time of the simulation, or the parameters themselves, the parameter that's shifted. So here we have the results. Again, the first model setting in which we simulate only one population while increasing the coupling gain. And here we have the feature series for variance, skewness, kurtosis, like one, autocorrelation, and mutual information for increasing values of stimulation amplitudes. And we can see that for one population, we don't see much of a trend as the seizure is approaching. But for the second population, we can see that for increased stimulation amplitudes, we can see that there are some trends for variance upwards and skewness and kurtosis downwards, and also a bit on the mutual information between them. And when we take a look at the Spearman's rank correlation, these bottom plots here, we kind of confirm these trends that for increased stimulation amplitudes, we have correlation of parameter and the feature. And now another model setting or configuration now stimulates both population sets. They have similar profiles as expected for both populations, and the increased it's way more visible. This change right before a seizure happens, and we also had to make sure that the simulation is not eliciting the seizures themselves. So we measured the onset time of the sustained discharges of spikes for every configuration, and we didn't find any changes. And now concluding, we have that in most model settings, the active probing approach indeed highlighted features that indicated these model parameter changes, but we had a local effect. That is, the changes that are not observable in features restricted for the populations that are not perturbed, not approached. And also some feature changes, such as increased leg one autocorrelation, variance, and mutual information, are common signatures of phenomena of critical slowing down. This might be related to approaching critical transitions, and it's still unclear if the onset of seizures involves such transitions. We have evidence both in favor and against it. And this might be another use for this active program approach of highlighting or telling us something about the dynamics of these transitions involved in from normal to ictal activity. And we have our preprint available, so I'm happy to take any questions now or later if you want to get in touch with me. Thank you.
Okay, thank you. Thanks a lot, Vinícius. Very interesting and somewhat related to the work that we are also doing in terms of predicting seizures. Are there any questions for you? If there are any questions, please type them in the Q&A box, or if the panelist wants to have question, they can actually ask live here. So, I mean, this is great. So one thing that I wanted to see on the last slide, you had critical slowing. So there was a recent work from which is coming out of the groups like Mark Cook and others, Levin Kuhlman, which talks about critical slowing as a biomarker.
Yes.
Yeah, so it's so can you, so I was just thinking that is it possible that you can actually replicate or show in your model that you can see critical slowing happening, or certain parameters which can replicate some of the work that they were showing?
We did this with other parameters. These are included in the preprint, but we saw these changes as well, the increased leg one autocorrelation, the variance, which might indicate that the response to the stimulation is getting more and more slower as the transition from normal to ictal activity is approaching. So for this model, we see that we have some evidence that this might be indeed the case. It will be interesting to test other models. I'm curious about models of absence seizure, for instance, if this will be the case. And and of course, test this with real data, with animal models that were we're in plans of doing this also.
So I mean, so I was just thinking what the main idea here is this, that if you can have in silico seizures, so if you understand how to generate seizures, then you would be able to, because then you know that how the dynamics changes in the pre-ictal state to the ictal state, and then you can use that insight and those characteristics, some of the features, which can then be used to do prediction of seizures beforehand with a certain, seizure horizon, or a prediction horizon, that you can develop a warning system. So that's basically where you are going, right?
Yes, exactly.
Okay.
And the model that Vinícius mentions, the peripheral variant, that's one goal that we have as well. We tested a similar approach on that epileptor model. That's from the same group, and the results are quite similar. But I really wanted to take this and put it on test it on the peripheral red brain.
Okay, thank you. Thanks a lot, Vinícius. While we have Vinith here, I wanted to just quickly